In this video, we're going to explain a distinction that often confuses students of the x86 architecture, namely the difference between the instructions MOV and LEA. Both of these are very useful instructions and ubiquitous in x86 programs. They're superficially similar, but the difference is crucial. First, let's recall that the x86 instruction set architecture contains a number of addressing modes, that is, ways of specifying data. One general form is shown here. This designates a memory address, often called the effective address, as an arithmetic expression of 4 values. D is a displacement, an integer constant. RB and RI are 2 of the x86's general-purpose registers. And finally, S is a scaling factor, which must be a constant, 1, 2, 4, or 8. The effective address is computed as D plus the contents of RB plus S times the contents of RI. For example, suppose that RBX contains hex value 100 and RSI contains hex value 200. And let's assume that the contents of memory locations 9, 10, and the next 7 addresses in memory are as shown here. You'll see why that's relevant in a moment. Now, consider the effective address expression shown here. By our evaluation rule, this is equal to 10 plus the contents of RBX plus 4 times the contents of RSI, which is 10 plus 100 plus 4 times 200, which equals 910. This is the effective address denoted by the expression. Now, let's use this same effective address expression within the following x86 MOV statement. This is a memory-to-register quad-word move. As we've seen, the first argument designates memory location 910, so this statement says to copy the 8 bytes beginning at location 910 into register RCX. Because the x86 is a little-endian machine, the resulting hex value in RCX will be what's shown here. No other registers will be affected. But let's suppose that instead of our MOV instruction, we had the following x86 LEA statement. By the way, LEA stands for Load Effective Address. The computation of the effective address in the source argument position is exactly as before. It designates hex address 910. But in this case, instead of using the effective address indirectly to fetch the contents from memory, we load the address itself into register RCX. That is, we assign 910 to RCX. Note the difference from the MOV statement. In both cases, the first argument is an address or pointer value. For MOV, we dereference the pointer to get the contents of the designated memory address. For LEA, we store the pointer value itself. Sometimes an LEA instruction is generated by the compiler for reasons other than address computation. It's used for doing arithmetic on values stored in registers. For example, suppose you wanted to compute the expression 8x plus y minus 5, where x is stored in register RAX and y in register RDX. Let's assume we want to leave the result in register RDI. The compiler might generate the assembly language statement shown here. As usual, the first argument is computed as minus 5 plus the contents of RDX plus 8 times the contents of RAX. We see that that evaluates to 8x plus y minus 5, which is the result we wanted. And since we're using an LEA instruction, that result is simply loaded into register RDI. Pretty clever, right? We've used a single assembly language instruction to compute an expression involving a multiplication and 2 additions. Of course, it's limited to multiplications by 1, 2, 4, or 8, but it's still often a useful trick. And notice that it really has nothing to do with effective address computation in this case. Finally, consider the following 2 assembler statements. Rightly speaking, neither of these should be legal, since the source argument is not an effective address. However, most assemblers allow these, rather than raise an error. In both of these cases, LEA is essentially identical to MOV. For the first statement, the contents of RAX are copied into RBX. In the second statement, the decimal constant 10 is copied into RCX.